let's see here. So if we calculate the Jacobian of G times the vector, so we put the vector x naught here and y naught there, right? That would be the value of the Jacobian at the point in question. But I guess I'm not doing that. I'm actually multiplying it by x minus x naught, right? And y minus y naught, right? But that's, so you just, this right here, this matrix right here is defined to be partial g, partial x. And this one over here is partial g, partial y. So with that notation, this matrix multiplication literally becomes
Why do we have the k plus that equals k again?
we're linearizing the equation. What's the linearization of the constant? Well, you just leave the constant, you know, vector. But this is by assumption k again, so we get that. So, sorry, I'm thinking. I'm trying to think how would I multiply. Well, anyway, so this works out to partial g partial x times the x minus x naught vector. So this is at the point, right? Times the x minus x naught vector, and then plus partial g partial y at the point times the y minus y naught vector. Right. Yeah. So, I mean, this is, let me just try to explain what's going on here. This is a n by m plus n matrix. This right here is a m plus n by 1, m plus n by 1 vector, because you got m for x, you got n for y, you're stacking them, that's what that is. When you multiply them, this is a n by 1 column vector again, all right? And by the calculation down here, that's equal to 0, right? And, well, it's approximately equal to 0 because, of course, this is the approximation, right? It's an approximation. And so, but approximately we can solve for y, and that should give us, well, when can we solve for y? What condition do we need? How do you isolate y there? We can solve for y equals to y naught, right? Minus what? Minus partial g, partial y at p naught, what? Inverse times the partial g, partial x at p naught times x minus x naught. So there you go. That's the first approximation to the implicit, implicitly writing y as a function of the x's. And then you can repeat this. And again, you can prove by the contraction mapping that there's a contraction mapping here, and that as such you get a fixed point of the sequence of functions, sequence of maps so defined, and that limiting function ultimately is the implicit function that defines y as a function of x here. But of course it all rests on the condition that we need the determinant of partial g partial y at our point, right? We need that to be not equal to 0. If we have that non-zero and we have continuous differentiability of the defining equations, well, by golly, we can then write all the y variables as functions of the x variable. And if you have all that, then you can define like x, right, as a mapping from Rn to Rn plus m by x of x vector equal to, well, x y of x, where that y of x is the implicit function that the implicit function theorem gives you. See, if you have this in hand, then all of a sudden you can view the solution set to this system as a n-dimensional manifold in Rn plus m, which is in some sense like a graph. This would be a generalization of the idea of graph when we have some of the Cartesian variables simply as functions of the remaining Cartesian variables. That's the generalization of the idea of a graph. Of course, not all parameterizations. I mean, locally, we can write this n-dimensional space as a graph. Now, this proof, sketch of a proof, I've assumed that the variables we wish to make dependent, right, are at the end of the list, and that the variables which are going to be the parameters, the independent variables in our solution, our implicit solution, are at the start of the list. But this is just a convenience of bookkeeping, right? Actually, the more complete statement of the implicit function theorem is that if you can pick any n variables in your m plus n variables, right? If you can pick any n variables and you concatenate the columns of the Jacobian matrix of the level function, the g vector. If you look at the n by n submatrix of their partial derivatives, if that's invertible, then you can solve for that set of n variables. But there's something more beautiful than this. There's another way of saying this calculationally. Actually, the truth is, you can take the total differential of these. You can take the total differential of each one of these equations. And if you can solve those equations for the differentials of n of the variables, it follows that those n variables can be written as dependent variables of the remaining m variables here. Let me try to illustrate that calculational principle with an explicit example. Like the method of differentials here it's really quite striking once you understand it. So let me show you something that, and again, the careful proof rests on the contraction mapping principle. We have to come back to it, okay? Yeah. I want to actually look at an example of this. Or try to anyway. So let's try to look at a three-dimensional manifold in a five-dimensional space. So a three-dimensional manifold in a five-dimensional space. That means I need two equations in five unknowns. So my two equations will be x squared plus y cubed plus z to the fourth plus w to the fifth. I need another variable, x, y, z, w. I guess I'll use a u. X, y, z, w. I'll put u last. I'll just put u like that, all right? Equals to 10, okay? And then for the other one, just to be annoying, I'll do something like xy plus yz plus z zu equals to, oh, I don't know, 0. All right, so let's say that basically, let me talk about this. So here I've got, you know, G1, G2, right? And if we want to think about it in terms of the nomenclature of the theorem I wrote, we've got G vector, which is a mapping from, like, you know, R5 to R2, all right? So I guess the first thing I could do, I really want to talk about the method of differentials, but before I do that, let me do the more sort of lowbrow, it's not lowbrow, but the sort of more obvious thing given our current discussion, which is to calculate the Jacobian of this map, right? And so, and when I'm working with examples like this, I like to do something like this, x, y, z, w, u, just to declare that's the order of the variables, because it matters, because that informs which partial derivative is which column.
Okay.
Yeah. And who's to say that u, v, w, x, y, z isn't the proper order of these, right? So, but it's what I did, so it's what I did. So that's 2x, my bad. You got yourself a 2x upstairs, you got yourself a y down here, you got yourself a 3y squared, you got yourself an x down here, plus z, right? Keep me honest. Then partial with respect to z, we've got a 4z cubed. We got ourselves a y plus u. And what else we got here? With respect to w, so you got your 5w to the fourth. Oh, there is no w in this equation, is there? Interesting. 0. Right? And finally, partial with respect to u, you got a 1 here, and you got a z down there. All right? So we can look at, like, partial g with respect to, let's say, you know, w and u. And that would be, you know, 5w to the fourth, 1, 0, z, right? So that means we can solve for w and u as functions of x, y, z, right? Given what? We need that 5w to the fourth times z is not equal to 0, right? As long as 5w to the fourth times z is not equal to 0, then that 2 by 2 matrix is invertible. Hence, the implicit function theorem guarantees the existence, at least locally, of an implicit solution to those equations. Let's see here, what else could we try? On the other hand, suppose you wanted to solve for, like, x and y. Well, then you would look at these two columns, right? And if you did that, well, it's kind of messier, right? What's the determinant of this? Yeah, we got 2x times x plus z minus 3y cubed. So there's some fairly complicated region of points in the 5-dimensional space where we cannot write, you know, so whenever, if this is not equal to 0, then we can write, you know, z is equal to z of xy. We can write w as some function of x and y. And we can write u as some function of x and y. I find this notation convenient with the understanding like that's function notation, as opposed to inventing letters for every new function I'm suggesting. Like, it's just nice to not have a plethora of new letters. If you understand what this means, I mean, it's okay. Yeah. So that's what I was talking about. It's like we did the proof for them being over here, but you could also have them here. You could also like do this and that, you know. Okay, but that's not the method of differentials I was talking about, okay? So the method of differentials I hope I moved the camera over here, did I?
I think so.
I think so. Okay, let's believe that I did that. As the alternative is depressing. All right. So so same example. All right. We've got x squared plus y cubed plus z to the 4th plus w to the 5th plus u equals to 10. And I've got xy plus yz plus zu equals to 0. So the other method to implement the implicit function theorem actually is to just take the differential of the equation and try to solve for the differentials that are in question. So like here, if I take the differential, I get 2x dx plus 3y squared dy plus 4z cubed dz plus 5w to the 4th dw plus du. And the second equation, I get myself y dx plus x dy plus z dy plus y dz plus u dz plus z du equal to 0. Now let's clean this one up a little bit. So I have y dx plus x plus z dy plus y plus u dz plus z du. Right, so we'll focus our attention on these two. This is equal to 0, of course, right? So look at this and look at that. Now our goal, our mission, should we choose to accept it, is try to solve for a pair of the differentials. So I guess I will do the easiest thing, which is to solve for the du. So, I mean, generally it's going to be a pain, but solving for du is pretty easy. Right? Right? That's my du. But let's see here. I could also solve this one for du, right? So I solve this one for du. They're equal. So I can then solve for dw, right? dw, let's see here. So we get 2x minus y over z dx. See that? Plus 3y squared minus x plus z over z dy plus 4z cubed plus minus y plus u over z dz, right? So I moved everything over to the other side here. Now I've got this pesky minus 5w to the fourth, which I will simply divide by. So this is my dw equation, and of course my du equation. I then can go and I can either use this one, but I think I like that one. So I've got du is minus y over z dx minus x plus z over z dy minus y plus u over z dz. All right? Now, what conditions did I need in order to solve for in order to solve for these differentials, right? The algebra I just had to do, I need what? I needed, certainly I need w not equal to 0. It looks like I needed z not equal to 0. I mean, that could have been illusory. Like, you know, sometimes you can assume, you can do division where, you know, an addition, where a subtraction would suffice, right? Like sometimes when we do algebra, we trick ourselves into thinking we need the division, but we didn't really. But I think here we actually do need it. And, well, isn't that interesting? When you go back over here, what did we need?
I felt
See it? Not an accident. Not an accident at all. But there's more. You see, if you do this method of calculation, all right, the meaning of the coefficients of the differentials are partial derivatives. You see, the fact that I've got this here tells me that partial w, partial x, all right, holding y and z as fixed, all right, it's equal to, you know, it's equal to 2x minus y over z divided by minus 5w to the fourth. That is the partial derivative. So, of course, if you start thinking about, well, what is a partial derivative? If you're holding x, y, and z as independent variables, well, the partial derivative with respect to x is when you basically make dy and dz 0, right? So this has to be the partial derivative because we basically have dw dx is the partial derivative with respect to x in the sense that you're holding dy and dz as fixed. And similar comments could be made about the other coefficients, right? Like this right here, what that would mean is partial u partial x. And we're taking the other variables to be y and z, apparently, and that's equal to minus y over z. Now this notation, where I'm announcing the independent variables, you don't always find that in calculus books, but I think it's a good notation to use. Some people don't make that explicit. I think it's a good habit to make it explicit so your reader knows what you're taking to be independent variables and what you're taking to be dependent variables. See, because when you just get a pair of equations, two equations with 5 variables each, it begs the question, which is dependent on which? And this isn't just an academic question, see, because if you study thermodynamics, in thermodynamics there's something like, I don't know, there's at least a dozen popular variables to describe the equation of state: temperature, energy, pressure, volume, number of particles, the free energy. There's more, okay? And there are equations of state that relate those things. And if you want to talk about how their partial derivatives are related, well, you differentiate the equations of state, taking the differential of them. And then this method of calculation will show you how to find partial derivatives of one of the state variables with respect to the other. So like, if you're studying thermodynamics, it is awash in partial derivatives and ambiguous equations in terms of which is a function of which, you know? So for physics, this kind of calculation actually matters a fair amount. So the other thing I haven't quite captured yet in what I've told you today is just how the derivative of the implicit function relates to like the derivative. Like there's a sort of like a chain rule in my notes about this. I think what I'm doing on page like 98 to 99 in the notes is essentially proving. See, because listen, I made a somewhat bold claim here, right? Which is that, if you just take the differential of the equations, then you're going to be able to solve for the differentials only if in exactly the same places where that determinant's non-zero, right? So the calculation I'm doing on pages like 98 to 99, I think is essentially the derivation of that claim. All right? And we should probably work through it. Probably that would be a good thing for us to do. Let me try to do that. So yeah, the other thing I haven't talked too much in here yet about is, can I erase? Yeah, let me. By the way, my favorite way to come up with examples in here for like functions to invert is to just take like complex variables examples and just convert them to real notation, because like the cube function from like the plane to the plane, it's very easy to invert if you know about the cube root function, the principal cube root function in complex, right? But imagine if you're just looking at that in real variables. It makes such a nasty homework problem, yes. So if you want to see through some of my harder advanced calculus problems, you can just kind of go, oh, he's just taken the complex formula for such and so forth, and well, that's nasty. See, the thing is, I can also create examples with my A calculus. Because the thing is, in the A calculus, it gets interesting for making examples for advanced calculus, because I have an inversion formula for the algebra. So I know how to find the inverse of an algebra thing. And so I can use that to come up with, I then know how, if I write a formula for a function on like R3 on the basis of a three-dimensional algebra, and I know the inverse for the three-dimensional algebra, then I can invert the equation using at the level of algebra notation. And it might be relatively simple for me to know that there's an inverse and to know what it looks like. Whereas slogging through that at the level of real notation could be really, really nasty. Those are my my meanest homework problems. But now I told you they're secret. But anyway, that's actually not much of a help unless I tell you which algebra I used. Okay, so let's try to look at the chain rule here, see if we make sure we understand what I'm saying about the total differential and all this, because all right, so here we go. We have, for example, g sub I, right, of x1, x2, dot, 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 x, how many is it, m? And then suppose we've got y1 of the x's, right? y2 of the x's, yn of the x's, all right? And that's equal to your constant, your ith constant, right? Okay, so I'm assuming that I already have the implicit solution for the y's in terms of the x's. Then the question is, what happens if I take the derivative of this? So like partial, let's talk about partial with respect to x, partial x. We'll do 1 just for the sake of specificity here of that. So what was the what does the chain rule look like here? So I use x and h of x. Maybe I should do that. Let me use h instead of y, so that we have. I don't want to. That will help us. That will help us make this make more sense. We'll drop the x vector. We'll just call it x without the index, and we'll do this h of x. Okay.
Which page is that?
This is page 98, I think, the bottom. All right, so the chain rule here says this is the sum I equals 1 to m of like, oh, I shouldn't use I. J equals 1 to m partial gi partial xj at the point, right, times partial xj partial x1, right, okay. I'm going to do the kth derivative because I think we can get away with it, okay? So that would be the kth derivative here. So, but this is a function of m plus n variables, so there's still more. There's still more, right? Plus what? The sum, let's say, L equals 1 to n of partial g, partial yl, partial, and then what is y equal to here? It's equal to h, all right? So I do h here, the lth component of h, partial xk. Does that make sense? I mean, I don't know if you're comfortable enough with the chain rule, multivariate chain rule. Like, let me help me. Would you help you for me to review it?
Sure.
If I had, for example, f of x of t s, y of ts, right? Z of ts, for instance, right? And if I was to calculate, for example, like partial t of that, the way that goes is I take partial f partial x times partial x partial t, right? Plus partial f partial y partial t, plus partial f partial z partial t. So the chain rule is like that. And maybe it's good for us to just take a second to appreciate why that is. Here I'm looking at a function from R3 to R, right? And then my xyz function is actually a function from what? From R2 to R3, right? So let me call this big G. So f prime, right? Well, the Jacobian of f is what? The Jacobian of f would be a 1 by 3. So the Jacobian of f is actually a row vector. In this context, fx, fy, fz. And the Jacobian of g on this one is actually a 3 by 2 vector. And so it's xt, yt, zt, xs, ys, zs in my current notation, right? And so if I calculate the product, see if I calculate, so this is what? This is f composed of g, right? Is what we're looking at. And so if I calculate the Jacobian of f composed of g, it turns out that that's the Jacobian of f evaluated at g of st, all right, times the Jacobian of g at st. And so here, that is explicitly, I'm going to drop the point dependence, okay? But this is fx, fy, fz, and then you got yourself xt, yt, zt, x sub s, y sub s, z sub s. So that is literally fx, xt, plus fy, yt, plus fz, zt, comma, fx, xs, plus fy, ys, plus fz, zs, right? And this is just the other notation for precisely what I wrote up here. So all of these chain rules, properly understood, can be derived from multiplication, matrix multiplication of the underlying Jacobian matrices. All of the plethora of chain rules that we see in Calculus 3 are all derivable from the simple fact that the differential of a composite is the composite of the differentials, and as linear algebra works, the matrix of the composite of two linear transformations is the product of the matrices composed, which in this case ends up being the product of the Jacobian matrices. So anyway, that's the backdrop. That's why this chain rule is what it is. And it just so happens here that we have a special notation for the first m columns versus the last n columns, because we're keeping with this notational scheme of anticipating solving for the last n variables, right? That's just a current notational gimmick. What happens when we calculate? Yeah, okay. So what's the differential of GI, by the way? By definition, okay, this is the sum I equals 1 to m of partial g partial xi dxi plus the sum, let's say L equals 1 to n of partial g partial y L dyl. That is the total differential. And I've missed my I. Oh, my bad. Yowzers. I guess I better change that to a K for now here, since I has a fixed meaning, right? But here you go. That's the total differential for G, right? And so I can just as well, I can just add these, right? I can add these. And instead of thinking of it like this, check this out. I can just think of it as a vector of differentials. But I'll put the vector on the G, right? I think that's a reasonable thing to do. Well, I'm a little worried about that step. I'm going to not do that. Sorry, I'm a little bit, I don't want to write nonsense. Okay, so then think about this. Then you've got, You got dg1, dg2, dgn, right? And down the line, right? So let's see here. I think if I add these equations, right? I think if I add all these equations, I could look at it as like the vector of the differentials for G is equal to like the matrix partial G partial X vector times dx vector plus partial G partial Y vector is dy vector, where the dx vector is literally just a vector of differentials, like x1, dx1 through dxm. And the dy is, again, a vector of dy1 through dyn. And these are those matrices we talked about before. And so, in view of this, of course, we can solve for dy is equal to what? Like, so first of all, this would be equal to 0 in this context because we're looking at the solution set of a system of equations, right? So that's 0. And the dy is going to be what? Well, it's going to be, partial G partial G partial Y, which, by the way, is a square matrix. So this inversion makes sense, at least in principle, if it's invertible. I mean, the point is it can be invertible because it's a square matrix. If I tried to invert a rectangular matrix, well, that would be trickier, right? But there it is. See that? That right there tells me what the partial derivatives of the y variables are in terms of the partial derivatives of the defining equations as they relate to the x variables. So like this up here, we're getting to that. See this? Like this is attacking the same issue up here with a different notation. All right, like this here. Just a second, I've lost my place. Oh, okay. Well, let me put myself out of my own misery for a second here. I'll just tell you. If you look at page 99, right, what I do, on page 99, right, what I do is I simplify this. Of course, you can simplify this, right? Like, for example, this right here, what is this? Well, that's the Kronecker delta JK, right? Which simplifies all of this sum down to just what? It's just partial G partial x what? Partial xk, right? This whole thing is just partial G partial xk. And I mean, this is what it is. So that's the first simplification I make. And then what I do is I just concatenate all those into one big matrix at the top of page 99. and then I rewrite it as the sum of two matrices, and then I point out that I can factor out the partial G partial Y matrix times the partial H partial X. Let's see here. So let me erase this over here. Maybe I can. Man, I tell you, these girls giggling, it destroys my thinking. All right, so let me put this all. So this, of course, is equal to 0, right? So what we have is, so I just make a matrix where I'm just like, well, I guess I could just do it this way. So I've got partial G partial xk is equal to minus the sum, right? L equals 1. This was for GI. Minus sum partial GI partial YL, L equals 1 to N, of partial HL partial XK. And I think what I did was I just basically stacked, like I concatenated these into a big matrix. So this is like, oh yeah, partial G1, partial X1, partial G, partial G. I don't need to put the I ranges from 1 to n, right? So drop the I, just this is vector, right? So I ranging from 1 to n gives me the first column here, right? And if you look at what's going on over here, we can just also sort of just stack those the same. Partial x, what was it, m, right? And that's going to be equal to minus, and I guess I can just keep the sum out here just to not write it a billion times. L equals 1 to n of like partial G vector partial YL partial HL partial, well, I guess I would do 1 to start with, right? And then the next one would be like partial G partial YL summed against partial HL partial X2. And this goes on until we finally get to the mth one, right? But then we look at this and we go, oh, okay, so this really is just, you know, we can rewrite that as simply like minus the sum L equals 1 to m, n rather, of the partial G partial Y matrix, right, times the partial H partial oh, good grief. Sorry. Times this, you know, partial H. Fine. Phooey. I cannot see it. I've chosen a different notational scheme in the notes, right? Slightly different. So I say I've just got partial H, partial X1, partial H. All right, so let me adopt. Let me not. I'm not making explicit the sum in the notes, and that's helping, right? So no, don't write that sum. Instead, so I said that basically this is saying partial G partial xk, right, is equal to like minus partial G partial Y times partial H partial xk. I think that's essentially what I did. And then I have that stacked over and over and over again. So I end up with just like putting that in column by column by column, and then using the matrix column property, I've got minus partial g partial y times the partial h partial xk, which then means I can solve for partial h partial xk as equal to minus the inverse of this matrix times the times the partial g partial x matrix, right? Now, so here, for example, h you can think of as being like y1, y2, da da da, yn, right? That's what the h is here. So this would say something like, to calculate, for example, partial y, partial yi, partial xk, right? We would have to look at, like, you know, basically that thing, right? This horrible thing, and you just look at the ith component of it, you know? There's a k here. Wait a minute, no. Huh? Am I writing nonsense? I hope I'm not writing nonsense. I may be writing nonsense. I've got partial h partial x in the notes. I think I've lost track of what h. Oh, that's a matrix. I should drop the k here. That's a matrix. So, but if I want to calculate the ikth component of the matrix, I probably should put I think I should put a k here. You see that, you understand, I did not, I mean, these are separate calculations, right? But we found our way back to the same expression. And like, so if I just look at a specific one here, that is going to be, my claim was that you can just calculate differentials and look at the coefficients, and it's going to be the appropriate partial derivative, right? So this, once I clean the notation up, proves it in the sense, at least in this application, right? In as much as the implicit function mapping theorem is concerned, if I follow through the chain rule on the defining equations and trace out how the partial derivatives of the implicit functions with respect to the variables x1 through xm are, well, then when I solve for their partial derivatives, I find out that they're basically given by the particular components of this matrix, which is exactly, and in the same order, what's said down here. So I'm not claiming that I've proved the method of differentials works in all cases, but I would just say this. The method of differentials, the idea that you can take an equation, take the differential of it, and solve for the differential and identify partial derivatives, that's just one aspect of the method of differentials. It's far more broad than that. But really, what underlies the method actually is a particular application of the implicit function theorem or the inverse function theorem. The beauty of the method of differentials is that it has essentially implemented the inverse or the implicit function theorem in the details of how you solve for the differentials. Like it's the same thing. But I think to prove that the method of differentials works is essentially just to sort through how the chain rule of the differentials can get sort of plugged into the inverse or the implicit function theorem as appropriate to your problem. That's how I see it. Now, I'm not sure I've made it that clear this year, but anyway. Of course, we still have not proved the inverse or the implicit function theorem, but at least I showed you an example or two today. Examples here, they're harder to come up with, you know. Anyway, I'm going to stop for now because I'm getting kind of tired.